this seems like a word by definition. It shows you like sort of like this. Yeah, it's like a line chart. It shows like what's the frequency of using over the ages. And for those words, it doesn't have any data. I don't think anybody
It's like whenever it's like
yeah, that's Indian guy. White guy, yeah, sure.
yeah, exactly. It's bad, but it's also
Well, you actually pay attention to what he's saying, like it doesn't make sense.
yeah, that's right.
Usually, like one search word, like I'm usually even very frustrated. Like I don't pay any extra attention that I have.
Yeah. It's like I've tried everything. That's so but it's like the opposite.
Smarter to understand that they stated that they are like it doesn't give me an idea like some like finding like how many things are there. And each number is a tiny number that has to be
Yeah, because I looked at the
I don't have to. I just figured that out like 5 minutes ago.
Okay, so before we start today, does anybody have any questions? All right, so today we're going to take a step back from counting. So mostly we've been looking at techniques for determining the sizes of sets, so sort of standard combinatorial questions. And we'll look at a sort of helpful technique that's used all over the place in many many proofs. It's a really simple thing, and again, although it's really simple, the difficult part or the exciting part is finding clever ways to use this really simple thing. And it's called the Pigeonhole Principle. And it says the following: if I have a bunch of holes, so I don't know, I think this comes from some time in the past when mail was delivered by pigeons. And so let's say I have K holes, and I try and take more than K pigeons and have them all fly into those holes, then something fairly obvious is going to happen. If there's more pigeons than there are holes, and every pigeon flies into some hole, then there's going to have to be a hole that contains more than one pigeon, right? And in particular, we're not interested in dissecting these pigeons or cutting them into pieces. So if a hole contains more than one pigeon, it contains at least two pigeons. Right? Is that surprising to anyone? So it's the simplest thing you can think of. So K in this thing is the number of holes, and K plus one or more, so more pigeons than holes. And what you conclude is that at least one of the holes contains at least two pigeons. So you have to have at least here and at least here, because sometimes maybe in this case you take 9 pigeons and fly them into these 8 holes, but you end up with 4 holes that have 2 pigeons, for example. So that's more than one hole that has 2 pigeons in it. or you take 9 pigeons and they all fly into one hole, in which case it's still true. You have at least one hole that has at least 2 pigeons, because the hole with 9 pigeons in it has at least 2 in it. But both of those are required. You can't say there is a hole that contains exactly 2 pigeons. That's not necessarily true. An equivalent way of stating this with sort of terminology that we've been using here is if I give you 2 sets, A and B, here's A, here's B, and the set A is larger, strictly larger than the set B, then there's no one-to-one function from A onto B. Right? The one-to-one function, remember, says, function says for every element of A, you map it onto some element of B, and one-to-one says that there should be no element of B that has 2 or more things mapped onto it. And I think you can see if the elements of A are the pigeons, the elements of B are the holes, and the function defines what are the, which hole does this pigeon fly into, then the fact that you end up with 2 pigeons in the same hole means that you end up with 2 things in A mapping onto the same thing in B. This partial function that we've defined here, so far it's one-to-one, but we can't complete it because there's this, we've used up everything in B. There's no place for this to go without breaking the one-to-one property. Again, really easy. And the generalization of this, which is not any more complicated, is if I say, take a whole bunch of pigeons now. So imagine, M could be a lot more than K. It could even be a lot less than K. It doesn't really matter. But let's say I just have M pigeons. And those M pigeons fly into K holes. Well, I can then say this M over K, this is the average number of pigeons in a hole, right? I mean, if I add up how many pigeons in each hole, I'll get M, and then I divide by the number of holes. That gives me the average number of pigeons in each hole. That's going to be M over K.
So K represents, so what's M, the number of pigeons?
M is the number of pigeons, K is the number of holes. So if the average is M over K, then there has to be something in here which is bigger than or equal to the average, because not everything can be smaller than the average. That wouldn't make sense. And finally, again, these are pigeons. We're not interested in slicing them or cutting them into pieces, so the number of pigeons is an integer. So there's one that contains at least M over K, which means that it contains the ceiling of M over K. Right, so if M over K is 2.5, for example, then there's a hole that contains at least 2.5 pigeons, which means the hole contains at least 3 pigeons. Is that all clear? Okay. So in this class, for example, not in this room right now, but enrolled in this class, there are about 394 students. Now, there are 365 days in a year. So what I can conclude is that there is at least one day of the year such that at least 2 students have that day as their birthday. Or another way of saying that is there's at least 2 students in this class who have the same birthday. Right? Because there's only 365 different days on which you can have your birthday. There's more than 365 students in the class, so there must be a pair of them who have the same birthday. A is the students, A is the set of students, B is the set of birthdays. Yep. For sure, here you need it because otherwise dividing by 0 doesn't make sense. And then it doesn't really make sense if the pigeons fly into 0 holes. Then it doesn't, that also sort of doesn't make sense. And similarly, for here, functions from A onto the empty set, somehow that doesn't work either. So you need at least one thing in B or one hole, however you want to view this. Yeah.
So I know this works for k plus 1 of pigeons. Imagine you have 2k plus 1 pigeons. I don't think you can say that like at least one column contains at least 3 pigeons.
Yeah, so if you have 2k plus 1 pigeons, and they all fly into k holes, then the average number of pigeons in a hole is 2k plus 1. Right? That number is bigger than 2. It's 2 point something, right? Because 2k over k is equal to 2. 2k plus 1 over k is bigger than 2. But the number of pigeons in a hole is an integer, and it's so now there's one of the holes has an integer number which is bigger than 2, which means you get the ceiling, so there is a hole that contains at least 3 pigeons.
What about like, yeah, you're right.
I mean, we can try it. Put 5 pigeons into 2 holes. Try that and see.
Are we going to do other things based on this?
Oh yeah. This is just the rule that we're going to start applying.
Because I want to make sure I understand this.
So the baby application was students in this room and birthdays. From that, we can conclude there's 2 students with the same birthday. Let's start with something a bit more convoluted. So this is called Simon's drinking problem. So here's something that I'm telling you. Simon drinks at least 1 beer every day. Simon drank exactly 45 beers in April 2019. And let's remember, April has 30 days in it. Okay. So that's all I know. Simon drinks at least 1 beer every day. He's a thirsty guy. And last April, he counted. He was able to stay sober enough to keep count, and he drank exactly 45 beers over the 30 days in April. Okay. So, the sort of obvious thing we can say from this is, well, Simon drank more beers than there are days. Therefore, there was 1 day that Simon drank at least 2 beers. Agreed? Because if he only drank 1 a day, then he would have only drank 30 beers. All right, that's sort of obvious thing, an easy thing to say about this. But here's something less obvious. Claim, and we'll need to prove this. There's a sequence. There was a sequence of consecutive days in April 2019. Such that Simon drank exactly 14 beers during those days. Now that seems like a crazy conclusion, and not at all obvious, right? Yeah, if Simon drank 1 beer every day for a while, then after 14 days, he would have drank 14 beers, and there's a sequence of consecutive days where he drank 14 beers. That's easy. But what if Simon drank 1 beer every day for the first 13 days, and on the 14th day he drank 2? Then I haven't seen a consecutive sequence of days in which he drank exactly 14, right? He went straight from 13 to 15. And so it's not at all obvious that this is true. So let's see if we can prove this. And we'll be able to prove this by the pigeonhole principle. I'm going to save, I think we can all remember what the pigeonhole principle tells us, at least the basic version. I'm just going to save the version with a sort of larger number of pigeons. And again, simple principle, clever application. For each I in 1 to 30, so for each day in April, let BI equal number of beers Simon drank on April I 2019. So B1 is the number of days he drank on April 1st. B2 is the number of beers he drank on April 2nd. B3 is the number he drank on April 3rd, and so on. And for each I in 1 to 30 as well, we're not only going to keep track of how many beers Simon drank on day I, we're also going to keep track of how many beers Simon drank leading up to day I, including day I. So we'll say let AI is equal to B1 plus B2, and so on, all the way up to BI. So that is number of beers Simon drank from April 1st to April I. Okay, is that all clear? All right. And finally, consider this sequence. A1, A2, A3, all the way up to A30. And then we continue with A1 plus 14, A2 plus 14, all the way up to A30 plus 14. So this is just a sequence of numbers. In fact, more precisely, it's a sequence of integers, because each of these things counts some number of beers that Simon drank, And when Simon opens a bottle, he finishes it. So there's no partial bottles here. Remember, this is about Simon's drinking problem. Okay? All right. So, how many numbers are in this sequence? This is an easy question. How many?
I would assume 30 numbers.
Yeah. So this is a sequence of length. There's this part, which has length 30. And then there's this part, which has length 30. So this is a sequence of length 60.
What does A represent? If B is the beers?
AI is the number of beers Simon drank on April 1st, plus the number of beers he drank on April 2nd, plus the number of beers he drank on April 3rd, and so on, all the way up to April I. All right, so this is a sequence of length 60. What's the smallest number in this sequence? Smallest number is, we don't actually know, but it's at least 1, right? Because A1, by this definition, A1 is actually B1, and Simon drinks at least 1 beer every day, so he drank at least 1 beer on April 1st, therefore A1 is at least 1. And, all right, so A1 is at least 1, and A2 is bigger than A1, and A3 is bigger than A1, because each one of them has to increase by at least 1, because he drinks a beer every day. Okay. So we know what the smallest numbers is at least 1, and maybe 2 is in there, maybe 3 is in there. What's the largest number?
Whatever AI is?
So what's the largest value of AI? Yep.
A30 plus 14.
So this sequence A1, A2, A3 is increasing because at each day he drinks at least 1 beer. So the largest value is A30. And therefore the largest value in the whole thing is over here. It's A30 plus 14. What's the value of A30? 45. Okay, because he drank 45 beers in April. So 45 plus 14 is what? 59. What a strange coincidence. The length of the sequence is k plus 1, and the number of different things that appear in the sequence is at most k. Right? I have 60 numbers written down, but all of them come from this set, which is only of size 59. So what can I conclude?
What's the sequence of consecutive days that he drank?
Too soon for that. What's the simple thing that I can conclude? I have more numbers than, so I have a list of 60 numbers, but all of them are in the range 1 through 59. So some number must appear more than once in the list, right? That's 60 pigeons flying into 59 holes. So, by the Pigeonhole Principle, and we'll call this, I'll write it down, A1 up to A30 A1 plus 14 up to A30 plus 14 must contain some number at least twice. Or another way to say that is, well, so some number in this sequence appears more than once. Okay. Now, that number that appears more than once, can both of its occurrences be in this first half, A1 to A30? No, because all A1 is smaller than A2, which is smaller than A3, which is smaller than A4, and so on. So none of the A's are equal. AI is not equal to AJ for any I not equal to j. Similarly, the number can appear twice over here for the same reason, because this is the same sequence just with 14 added. Okay. So that means, therefore, there exists I and j such that AI is equal to AJ plus 14. That's the only thing that can happen, right? Some number shows up here on the left half, and the same number shows up here on the right half. Because nothing shows up twice in the left half, and nothing shows up twice in the right half. Okay, AI is equal to AJ plus 14. Well, if I rewrite that, that's the same thing as saying that AI minus AJ is equal to 14.
What's AJ?
What's AJ? AJ is the value of, it's one of the numbers in the sequence. It's the number of beers Simon drank up to and including April J.
Oh, okay, like AI plus 14, or what's I and what's j?
So I and j are just two indices, as I know by the pigeonhole principle that something on this side is equal to something on this side. Let's call the thing on this side AI, and the thing on this side is AJ plus 14. Okay, so let's see what that means. So which one of these is bigger, I or j?